Hello guys, this video is on the necessary and sufficient condition for the weak convergence of a sequence xn in a normed space X. Now given a sequence xn in a normed space X, what is the necessary and sufficient condition for its weak convergence? So there is a theorem that gives this necessary and sufficient condition, and in this video we discuss this necessary and sufficient condition of the weak convergence of xn. Now the theorem states, let xn be a sequence in a normed space X, then xn converges to X weakly if and only if these two conditions holds. A, the sequence xn is bounded. B, for all f belongs to M, a total subset of x dash, f and x converges to fx. So this theorem, it gives the necessary and sufficient condition for the weak convergence of sequence xn. Now this theorem is if and only if case. So the proof of this theorem consists of two parts. Now let's move on to the proof. First, suppose xn converges weakly to X. Then by definition of weak convergence, for all f belongs to x dash, fxn converges to fx. Now since M is subset of x dash and this holds for all f belongs to x dash, this also holds for all f belongs to M. So for all f belongs to M, fxn converges to fx, and this shows this statement 2 holds. Now for the statement A, since xn converges weakly to X, xn converges weakly to X, by the convergence we have convergence implies boundedness, so xn is bounded. Now conversely, suppose the statement A and B holds, we have to show that xn converges weakly to X. Since the statement A holds true, that is, since the sequence xn is bounded, we can find a positive number C such that norm of xn is less than C, and for sufficiently large C, we have norm of x is less than C. Now since M is total in X dash, by the definition of total subset, we have x dash equals to closure of span of M. So that means if f belongs to x dash, then f belongs to closure of span M. Now by the property of a closed set, we have for this f belongs to this closure of span M, we have there exists a sequence fj in span M such that fj it converges to f. Now by the convergence, for a given epsilon greater than 0, we have this statement. And moreover, since fj belongs to span M, from the statement B, we have fjxn converges to fjx, and by the convergence, for a given epsilon positive, we have this statement. Now finally, we find a natural number capital N such that for all small n greater than capital N, we find this n from the above two convergence cases. From this convergence, we can find a natural number n1, and from this we can find a natural number n2. Now the minimum of n1 and n2, then for that n1 minimum of n1 and n2, this both convergence holds true, and let that minimum be this capital N. Then for this n, we have this statement, fxn minus fx equals to, we add this from, subtract this from, add and subtract this from, then apply the property of absolute value, which equals to greater equals to this one. Now since fj converges to f, we have this one is epsilon by 3, and since fjxn converges to fjx, we have this statement, and again since fj converges to f, we have this statement, and finally we have for all n greater or equals to capital N, fxn minus fx less than epsilon. That implies f of xn converges to fx for every f belongs to x, and this shows the sequence xn converges weakly to X. The theorem is proved. Thank you.